Today we're going to talk about exponents and logarithms. And we're going to cover quite a bit of content in this lesson. So feel free if you want to, watch it kind of in a watch it casually the first time, and then you could watch it a second time and a third time to try to get all of the details closer. But it's definitely something that is probably going to take more than one watching to really understand all the details. So to begin with, we're going to talk about exponents. So if I want to multiply 5 by itself 10 times, so I want to multiply 5 by 5, but I want to do it 10 times. I could write it out like this. 5 times 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 5. Right? There's 10 fives there. Right? That's something I could do. But that's kind of tedious. It's very annoying. All right, so what exponents allow us to do is it allows us to write things like this in a much more compressed way. So instead of writing 5 times 5 times 5 and so on and so forth, I can write 5 raised to the 10th power, and that means the same thing as 5 times 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 5. Okay, 5 to the 10th power. And so that's what an exponent is. That 10 up there is the exponent or the power. Some other examples of exponents is that we could have 2 to the 3rd power, so 3 is the exponent, and that is 2 times 2 times 2, or 8. Okay. So another one is 6 to the 7th power. So 6 times 6 times 6 times 6 times 6 times 6 times 6. And that's 279,936. You can also have 10 raised to the 5th power. That's 10 times 10 times 10 times 10 times 10. Now, one thing that's interesting when you raise 10 to a power is you basically get 1 followed by that many zeros. All right, so here we have 1 followed by 5 zeros. So that's going to be 100,000. You can raise decimal points to a power. I can raise 1.3 to the 4th power. That's 1.3 times 1.3 times 1.3 times 1.3. And that result is 2.8561. Okay, so I can raise a number to a power. The power is also called an exponent. And that basically says take the number and multiply it by itself that many times. Now, there's also a couple of special situations in exponents. First of all, anything raised to the 1st power is just itself. All right, so 27 raised to the 1st power is 27. Okay, so anything, if I raise it to the 1st exponent, even though there's nothing for it to be multiplied by, so it's just itself. Okay. One that's a little bit more surprising is that anything raised to the 0th power is actually 1. Okay, so 15 raised to the 0th power equals 1. And we could talk about what that means and why that's important. The way to think about that is if you think about a string of multiplications. So if we had something raised to some power and something else raised to another power and something else raised to another power, and if one of those were to be absent, rather than treating it as a 0, which would make the whole thing 0, you treat it as a 1, which makes it basically not have any effect. Okay, so we say anything raised to the 0th power is 1. So if that doesn't make sense to you, just remember the rule, and just if you have a 0 in the exponent, then the answer is 1. So then you can also have negative powers. And the negative power is very similar, but it means that the final value goes into the denominator. So for example, if I have 3 to the negative 4th, that's very similar. So if I had 3 to the 4th, that would be 3 times 3 times 3 times 3, okay, which would be 81. But if I have 3 to the negative 4th, that means all of those go on the denominator. So it's 1 over 3 times 3 times 3 times 3. So it's 1 over 81. Okay, so that's what a negative power means. It means that it goes in the denominator. Okay, so now so we're going to talk a lot about exponents. So as we talk about exponents, we're going to need some vocabulary about exponents. So let's look at this exponential expression. 7 to the third equals 343. Okay, so to start with, we've got the base. So that 7 is known as the base. Okay, whatever thing that you're raising to a power is the base. So the little number on top is the exponent or power. Okay, that's that little 3 there. We write it in kind of a smaller font and raise it up, and that's the exponent or the power. Okay, and then what it's equal to is the value or the result. Okay, so 343 is our value. So those are the parts of an exponential expression. Okay, and let's take a minute to really look at that, because we're going to use this in our next example. So it's important for you to really pay attention to each of these parts. So 7 is the base, 3 is the exponent, and 343 is the value. Because next what we're going to look at are logarithms. And logarithms tend to freak people out. Most people are pretty okay with exponents, but the logarithms tend to freak people out. But the thing about logarithms is that they are literally just the undo operation for exponents. So most math operations have an undo operation. So if you think about addition, it has subtraction as its undo operation, and subtraction has addition as its undo operation. Multiplication has division as its undo operation, and division has multiplication as its undo operation. So along with these, the logarithm is the undo operation for exponents. The logarithm says, given a particular value and a base, what would the exponent be that would raise that would give that value if you raise the base to that exponent would give you the value. Okay, so that's kind of hard to understand in words. So let's paint you a picture. So we're going to go back to our the logarithm we were looking at, or we're going to go back to the exponential we were looking at earlier. Okay, and so we have 7 is our base, 3 is our exponent, 343 is our value. Okay, so a logarithm that represents kind of the same idea would be structured like this. The log base 7 of 343 is 3. So again, we have our base, we have our value, and we have the exponent. So it's saying that given this base, given a base of 7, what exponent could you raise the base to give you the value of 343? Okay, and so the result is 3, because if we raise 7 to the third power, we get 343. So logarithms ask the question, what exponent applied to the base will yield the given value? Now we're going to look at some example expressions of exponentials and what kind of the equivalent expression is with logarithms. Okay, just to give you a better feel for the relationship between exponentials and logarithms. So to start out with, we're going to have the exponential 2 to the third equals 8. Okay, so if 2 times 2 times 2, that's 8. Okay, well the equivalent logarithm is a log base 2 of 8 is 3. That says what power do we raise 2 to in order to get 8? And the answer is 3. 5 to the second power is 25. Okay, so equivalently we could say log base 5 of 25 is 2. So what power do we raise 5 to get 25? And the answer is 2. 3 to the third is 27. So 3 times 3 times 3, that's 27. So we can also say what exponent should we raise 3 to in order to get 27? And the answer is 3. 4 to the first power is 4. So then you could also ask, what power should we raise a base of 4 to get 4? And the answer is 1. So the log base 4 of 4 is 1. 9 raised to the 0 power is 1. That's one of our special rules, that anything raised to the 0 power is 1. So then we could say log base 9 of 1 is 0. So in other words, what power do we need to raise 9 to in order to get the value 1? And the answer is 0. We can also do this with some of our more special cases. 4 to the negative 2 power is 1 over 16. So remember, the negative powers means that the result goes in the denominator. So 4 to the negative 2 is 1 over 4 times 4. This is 1 over 16. So we can also say log base 4 of 1 over 16 is negative 2. Okay, so that's kind of the relationship between exponents and logarithms. Now, one thing to keep in mind, even though we've been doing this with whole numbers, exponents can be decimals too. So it's not quite as easy to imagine what a number raised to a fractional or decimal power would look like. However, we can see that if 2 to the third is 8, because 2 times 2 times 2 is 8, and 2 to the fourth is 16, because 2 times 2 times 2 times 2 is 16, then 2 to the 3.5 power, it must be somewhere in between there. So you can put this in on your calculator, and the calculator says that 2 to the 3.5 power is 11.3137 and continuing. Okay. So you basically get decimal powers through your calculator. You might ask, how does the calculator do that? And there is an answer to that, but it actually involves a little bit of calculus to understand it. So it's not quite where we're at. So if you have a decimal power, you can just use your calculator to put it in. So since 2 raised to the 3.5 power is 11.3137, then we can also say that log base 2 of 11.3137 and continuing equals 3.5. Okay. Now, one thing to keep in mind is that when you use your calculator for exponents and logarithms, it is not unusual for your answers to be off by the rightmost digit. So whatever your furthest decimal point out is, sometimes you're off by that amount, and that's just because these numbers, in theory, go on forever, and your calculator doesn't have an infinite amount of memory, so at some point it just has to cut it off. So you should always expect that anytime you're doing exponents and logarithms with your calculator, that there's going to be some small amount of error available. But nonetheless, it's worth it because calculators are a huge help when computing logs. And the tiny bit of error that you introduce by using a calculator is more than offset by the ease of doing so. Now, exponents and logarithms have their own manipulation rules. They have a lot of rules attached that help you manipulate expressions, especially when you have variables in the logarithms. We're not going to cover a lot of variable logarithms in this lesson, but these will come in handy a lot later on. So some exponent manipulation rules. So a raised to the b plus c power is equal to a to the b times a to the c. Okay, so an example of that. So let's say we have 5 raised to the 2 plus 3 power. Okay, So if 5 is raised to the 2 plus 3 power, that's the same as saying, 5 to the 5th, because that's what 2 plus 3 is. It's 5. Um, and so that's 5 times 5 times 5 times 5 times 5. Well, we can use our uh, multiplication rules, which say that we can, the associative rule says that we can regroup these any way we want. And you can see that 5 to the 5th, that's the same as you can group 2 of the 5s together and then 3 of the 5s together. And that's the same as 5 squared times 5 cubed. So 5 to the second power times 5 to the third power. And those are the same thing. And so that's kind of an illustration of the rule above. Whatever your a is, a raised to the b plus c power is equal to a raised to the b power times a raised to the c power. Okay. So another rule, a to the b raised to the c power is equal to a raised to the b times c power. So to see this, let's take 4 to the third and raise it to the second power. Okay. So 4 to the third raised to the second power means that whatever 4 to the third is, we're going to multiply it by itself. Okay, so that's going to be 4 to the third times 4 to the third. Well, what is 4 to the third? Well, 4 to the third is just 4 times 4 times 4. So if we break this out, 4 times 4 times 4 times 4 times 4 times 4. So that's going to give you 4 to the sixth. Okay, so you can see, so 4 to the sixth, 6 is simply 3 times 2. Those are our powers multiplied by each other. So 4 to the third raised to the second power is equal to 4 raised to the 3 times 2 power. And note that this only works if it's 4 to the third grouped raised to a power. It does not work if the 3 raised to the second power was grouped. So the grouping is important there. So another one, if you have a times b raised to the c power, that's equal to a raised to the c power times b raised to the c power. So to see this, imagine we have 2 times 7 raised to the third power. Okay, well, that's just the same as saying 2 times 7 times 2 times 7 times 2 times 7. Well, we can use the associative and commutative laws of multiplication, and we can rearrange these so we put the 2's together and the 7's together, and we'll get 2 to the third times 7 to the third. Because notice we get 3 2's in there, and we get 3 7's in there, so that's going to be 2 to the third times 7 to the third. So our next rule is a to the b over a to the c equals a to the b minus c. And so that might be a surprising one, but we can see that if we have 3 to the fifth divided by 3 to the third, well, that means we're going to have 5 3's multiplied by each other on the top, and we're going to have 3 3's multiplied by each other on the bottom. So that means that all the ones on the bottom will cancel out ones on the top. And so we will subtract the powers. And that will give us, 5 minus 3 is 2, so we're going to wind up with 3 squared at the end, which is going to be 9. And this even works if you wind up with negative powers, because what does a negative power mean? It means that we're going to have the thing that we're multiplying together on the bottom. So if we have more multipliers on the bottom than we do on the top, that'll give us a negative exponent, which simply means that we're going to have the leftover exponents on the bottom. Okay. Now the thing also to keep in mind, this does rely on it's a to the b and a to the c. This doesn't work if you have a different base in each one of them, right? So if I had a to the b over c to the d, well, I can't do anything with that. It's just because they're both the same base, that's why I can do the subtraction. Okay, so those are our exponent manipulation rules. We have logarithm manipulation rules. And we're not going to go into examples of these as clearly as we did in the exponent rules, but most of these you can actually infer from the exponent rules. But we're just going to present them as is for right now because we're giving you enough information as it is. So the first one is kind of basically our fundamental definition of a logarithm. And that is log base A of A to the B equals B. Because what is a logarithm? A logarithm, this is our fundamental definition of a logarithm, because a logarithm simply means what value, if you raise the base, or what exponent do you need to get the value if you raise A to a given power? And so if you have log A of A to the B, well, the answer is just going to be B. Okay, so that's the fundamental definition. Okay. So then you have, this is kind of a corollary, log base A of A is going to always equal 1. And think about this. So A itself is just A raised to the first power. So if I want to say what value, what exponent do I raise my base to get my base, it's always going to be 1. And then a similar one, A raised to the log A of B is equal to B. Okay. So these are all just kind of variations of our fundamental definition of a logarithm. So our next one is actually very handy when you have, if you're trying to get rid of an exponent. And this is the fact that logarithms convert exponents to multiplication. So if I have a log base A of B to the C, notice that my base does not have to match what's in parentheses. So if I have a logarithm and I have some value raised to some exponent, I can actually move that exponent out front. So that comes in handy a lot if I'm trying to get rid of exponents. So if I want to solve an equation and I've got x in my exponent, well, if I take a logarithm of both sides, well, the exponent will then come down and be a multiplier rather than being in the exponent position. And it's a lot easier to work with. Another one is that logarithms convert multiplication to addition. And so if I have log base A of B times C, that's equal to log base A of B plus log base A of C. Then there's logarithms convert division to subtraction. So log base A of B over C is equal to log base A of B minus log base A of C. And then you have the final one, and I like to call this the calculator rule, although I think technically it's the change of base formula. But I call it the calculator rule for reasons that will become apparent very shortly. And that is the log base A of B is the same thing as the log base C of B divided by the log base C of A. So this is a super important rule. So pay attention to this one. The log base A of B is equal to the log base C of B divided by the log base C of A. Okay, so what this means is that I can use other logarithms to find out the logarithm of interest. Okay, so let's go into this more deeply. So our calculator rule. So why do I call it the calculator rule? Well, not all calculators can do logarithms of any base. Most calculators can do some logarithms, but not all of them. Some of them have the fancy little logarithm button that allows you to type in what base you want, and that's great. I hope you have a calculator like that. But there's a lot of the simpler calculators will only have 1 or 2 logarithms available. So if your calculator just has a log function, and it doesn't allow you to put in a base, and it doesn't have a base mentioned, that's probably using base 10. Okay, a lot of them will actually say log 10 on them to be clear. But if you just have a log function, it's using base 10. Okay, another log function that you might have is known as ln. Okay, and that's known as the natural log. And so that uses a special base e, which is this really weird number. You you don't have to know why that's important now. This is a number that comes up dealing with interest rates and dealing with calculus. But usually calculators, it comes in really handy in upper level math. So calculators oftentimes will have a natural log function, and that just means that the base is this really weird number e. Okay. Um, so a lot of calculators will just have one or two of these, but the nice thing is that so you might need to do a logarithm of a base that your calculator doesn't have. Well, the calculator rule says that if your calculator doesn't do a specific base that you're looking for, well, we can use the calculator rule instead. Okay, so let's go look at the calculator rule again. Calculator rule is log base a of b is equal to log base c of b divided by log base c of a. Okay, so for example, let's say that my calculator only has log base 10, but I want to know the log base 7 of 30. Well, the calculator rule will let me rewrite this. Okay, and here's what it looks like. So the log base 7 of 30, using the calculator rule, since my calculator has log base 10, I can write it as log base 10 of 30 divided by log base 10 of 7. Okay. So whatever logarithm my calculator has, I can rewrite this log in terms of the logarithms that I have on my calculator, because I just do log base whatever my calculator supports of the value divided by log of whatever base my calculator supports of the base I actually wanted to use. Okay, so in this case, it's 1.477 and so on, divided by 0.845 and so on and so on, and the result is 1.747869 and so on and so forth. So this is how you can use your calculator, even if your calculator doesn't allow you to put arbitrary bases in. It allows you to calculate the logarithms of any arbitrary base, even if your calculator doesn't support it. So some more calculator rules examples, and for all of these, we're going to use base 10 or base e, since that's what your calculator probably has. But the rule itself, you can use any base for it. It's the calculator rule because your calculator is probably base 10, and so that's what you'll have available. So start out, log base 4 of 16. So think about how would you put that into your calculator using the calculator rule. Well, you take the log, so you do the log base 10 of 16 divided by the log base 10 of 4. Okay, and so when I plug that in my calculator, I'm going to get this decimal number. Now, if you look at the actual logarithm, log base 4 of 16, what number or what exponent do you raise 4 to give you 16? You should probably already know the answer. It's 2. Okay, so anyway, so the question is, will this give us 2? So if you look and you divide these out, you do in fact get exactly 2. Now, again, as I said, when you do logarithms and exponents on your calculator, you shouldn't always expect an exact result. Sometimes they'll be off by just a little bit, and we'll see that in our next example. So here we're going to do the same logarithm, but this time, instead of doing log base 10, we're going to use the natural log, which again uses that funny e base. Okay, so the log base 4 of 16 is equal to the natural log of 16 divided by the natural log of 4. Okay, this is what our calculator rule says. We don't have to, whatever base our calculator supports, we can use. We just do the log with that base of the value we're looking at and the log with that base of the original base that we wanted to use. Okay, so here, this gives us 2.77259 divided by 1.38629. And if we do that division, then you get 2.00001. Okay, so it gets very close, but it's not exactly the same answer. Okay, as I said, you might be off by just a tiny decimal point when you do calculator-based exponents and logarithms, and that's fine. So another one is log base 2.8 of 3.95. Again, we can use anything we want as the base. So we'll convert that with a log base 10. We do log base 10 of 3.95 and log base 10 of 2.8. That gives us 0.59660 divided by 0.44716. And that gives us a result of 1.33420. Likewise, I can do the same thing, but I can do it with natural log. So natural log of 3.95 divided by the natural log of 2.8. That's going to give us 1.37372 divided by 1.02962. And that's again going to give us 1.33420. And so you can see that we're getting the same answer because of our calculator rule. The calculator rule says that it doesn't matter which base your calculator has, as long as you do the logarithm of the value divided by the logarithm of the base you wanted to use, it will give you the right answer. Okay. So in summary, exponents allow us to express the concept of a number multiplied by itself a certain number of times. The parts of an exponential are the base, the exponent, and the value. So for example here, 2 to the third equals 8. 2 is the base, 3 is the exponent or power, and 8 is the value. Logarithms are the inverse or the undo operation for exponents. They say, what exponent would we need to get the given value using the given base? So again, the log base 2 of 8 is 3, because what exponent would we need to raise 2 to in order to get 8? And the value is 3. The exponent that we would need is 3. So we went through many rules of exponents and logarithms that are based on common sense about exponents and how these can be manipulated and arranged. And then the most important one we went through was the calculator rule. The calculator rule allows us to calculate logarithms of any base, even if your calculator only supports logarithms of a particular base. And so that is the log base A of B is equal to the log base C of B divided by the log base C of A. So whatever base your calculator supports, if you're going to have base 10, base E, base 2, whatever your calculator supports, you can use for that C. You just have to do the log with that base of the value divided by the log with that base of the original base you wanted to use, and that will give you an equivalent result.